Thank you. Very nice to be here. My name is Simon Steele. I'm at the SETI Institute, which is in Mountain View, California. And I'm also the principal investigator, the PI for the NASA Community College Network. I'm going to say a little bit about NCCN, as we call it, and then I'm going to hand over to my colleague Vishal, who's going to talk a little bit about the ARDC-funded program to bring radio astronomy into community college classrooms. I thought we'd just start with a lovely view of the Milky Way galaxy. This is an optical image looking towards the constellation Sagittarius, which is the center of our Milky Way. What you'll notice in a visible image is it is a very dusty place. It's very difficult to see through these dust clouds using visible wavelength light. And that's one of the reasons why radio astronomy, radio waves, is so essential in looking deep into our Milky Way galaxy, because the extinction is much less at radio wavelengths. So that's one of the motivations for using radio astronomy in studying our galaxy. Now, we are inside our galaxy. It's 300 billion stars, including our sun. How can you tell the structure or the layout of our Milky Way if we're just looking from the inside out? One of the thoughts is that it probably looks like a lovely spiral. This is another galaxy. This isn't our own. This is NGC 16 or 1566. Maybe this is what our galaxy looks like, but we can't tell because we can't get outside. We can barely get outside our solar system, let alone getting outside our galaxy. And that's where radio astronomy comes in, because you can probe the depths of our galaxy, you can look at the dynamics of our galaxy, and from that you can get an understanding of the structure. And that's what was done back in the 50s, initially. This is an early map of the structure of our Milky Way. It was made by Jan Oort in 1958, using the 21 centimeter line, which is the spin-flip transition of neutral hydrogen. The parallel and anti-parallel spins and the transition between them at the hydrogen and electron that gives an emission at 21 centimeters or 1420 megahertz. Now, by looking at this spectral emission at different locations in our Milky Way galaxy, looking at the Doppler shift of that 21 centimeter line and its location in different galactic longitudes and latitudes, you can develop a picture of the spiral structure of our Milky Way. And that was first done in the 1950s. This is an experiment that could be done very nicely if you're in a 4-year research university. You have access to your own radio telescope, you have nice labs, but it's not the case if you are taking astronomy or taking physics at a college that does not have those resources. And that's where the NASA Community College Network comes into play. NCCN is a NASA-funded 5-year program to try and support the teaching of astronomy at 2-year and community colleges throughout the US. And the motivation for those of you who know the structure of community colleges is quite clear. About half, almost half of students taking introductory astronomy do so at community college. So this is a very, very large population. That makes about 700 colleges throughout the US teaching introductory astronomy. What's important, though, is that the resources for most of these colleges, not all, but most of them, are very, very limited. And yet they're reaching an incredibly important demographic in the United States. If you look at some of the stats here, 26% of the students are Hispanic, 13% Black, 29% of first-generation college goers, and 15% are single parents, and a lot of them are mature students who are coming back to get some sort of formative education and will need to take a STEM course, and that's where the astronomy course comes into play. So helping these students in an underfunded environment are instructors of whom only 23% actually have astronomy degrees. So this is the motivation for NCCN as a program to support these instructors to reach this incredibly important part of our community in providing a very, very authentic and powerful STEM education to create a science-literate workforce and population. NCCN works in 4 main ways. It provides a set of ready-to-go resources that these instructors can use for their classrooms. And one of those, of course, is what Vishal is going to talk about in a little bit. The second one is to provide professional development, actually get modern cutting-edge astronomy and space science developed by NASA into the hands of these instructors, so they're not just working from 20-year-old textbooks. The third one is we actually bring one-to-one contact between NASA subject matter experts and those community college instructors, either for the subject matter experts to give presentations to the students, or simply a one-to-one interaction and conversation between the scientist and the teacher to help them through some of the more complex, perhaps, topics that they have to cover in these astronomy courses. And the last one is providing a community of practice. Some of these colleges only have one astronomy lecturer. They have no community, they've got nobody to bounce their ideas off of. And NCCN provides that community for them. This is a map of the reach of NCCN. We are currently working with 206 community college instructors in 38 states around the United States. This is from our website. You can get information on our website from our booth, the SETI Institute booth. All of these are clickable, and you can find if there's a community college near you. The little blue rocket ships are the subject matter experts, the scientists, such as Vishal, who are helping us provide these instructors with very, very important resources. And these SMEs come from all of the NASA centers, most major universities and observatories. That's NCCN. This is a way to reach an incredibly important audience. And when Vishal approached the NCCN team, saying, I would like to develop radio astronomy to put that into the hands of these community college instructors. My first thought was, that is amazing. I love the idea. But we don't know if the instructors will be interested in this. They tend to be very overworked. As we said, only 23% of them actually are comfortable teaching astronomy. And generally, the courses that they're doing are packed with a lot of material. Will there actually be availability of time to learn about radio astronomy and teach radio astronomy? And to our wonderful joy, there was a huge response from the community college community to take part in this pilot program. It was selected up down to 44 community college instructors, of whom 6 were given the opportunity to come to the Allen Telescope Array in Northern California to actually do a hands-on workshop on the development of this curriculum. I'd like to call that Joel Isucker at the back there, who's also part of the program. And Vishal will say a little bit more about his work as well moving forward. That's just the background of who we're working with and why it's important. And I'm going to hand it over now to Vishal to actually talk a little bit about the program that we offered them.
Thanks, Simon. And thanks for the organizer to also giving us this opportunity to talk to you all about this thing that we are very excited about, is bringing radio astronomy to community colleges. So before I begin, maybe because I'm slightly an outsider, I also like to introduce myself. So I'm an astronomer. I work on various different subtopics, mainly involving compact objects like pulsars, fast radio burst, but I also am quite interested in machine learning techniques and large data and real-time signal processing. But apart from all, my main area of research is SETI. So I am one of the alien hunters. So you're going to talk about how do we find aliens, talk to me. I'm going to tell you a little bit about it today as well, but yes, that's one of my primary area of research. So, as Simon mentioned, in a STEM education, there are a couple of challenges, and these challenges are sort of further amplified in community colleges. So what are these? So first of all, motivating student and increasing their participation in your teaching is a challenge. You want to also bring theory and practice together is also a challenge. How do you utilize cutting-edge technology like what we are talking about here in this platform, right? How do we bring that to colleges? Are there there need to be an interdisciplinary approaches, because many colleges are teaching subjects that are not sort of overly common across all of them. So how do you design something that's applicable to large different areas of research? Also, the curriculum needs to be updated, because if you go to a community college and look at their curriculum, the content in there is like a decade old. It hasn't been kept up with time. So you also need some mechanism through which you can update the curriculum so that it can also increase students' engagement. So I'd just like to highlight a very simple thing. This is what I think historically people who have worked on the education, they all know about this thing. It's called Edgarsdale's sort of learning cone. What it shows you is that going from top to bottom is the sort of level of retention among students or among anybody. Like what level of retention, if something new is taught to you, at what level will you be able to retain that information? And as you go down at the bottom, that's the highest level of retention, and that's when you actually able to do stuff by hand. So if you are able to engage students of doing things by their hand, it increases their participation, it increases the retention. So you can increase, basically, if you want to convey certain ideas, you want to teach something, it's always better to let them do these things by their hand. So since we are talking about GN Radio, my entire talk will be building this particular blocks. So I'm going to talk about various different problems that I just mentioned. This is my problem statement. Like there are these challenges in STEM. How do we solve it? So this is our source block. Let's move ahead. So in order to solve the problem, this is not something that is new. People knew about it. There has been studies done among students. So there was this study done in a couple of years ago where they surveyed students and they asked this question: what excites you the most? What question in STEM education basically can create largest amount of sort of interaction? And undoubtedly the answer came: searching for life. If you talk about searching for life outside the Earth, searching for extraterrestrial intelligence, that increases the participation. Don't have time to go into detail, but the x-axis here is showing the amount of interest, and the y-axis is showing you different countries. And you can see almost all countries, across different geographical background, with socio-economical background, everybody is interested in sort of talking about searching for life in the universe. So if you can tie a complicated idea that you want to teach students with sort of searching for life, it always going to help you get that idea across pretty easily. So that was our sort of concept, and we pitch it to ARDC, and I'm very thankful for them to kind of support us for this pilot grant, where we were able to basically build a curriculum for community colleges with the SETI as a backdrop using GNU radio module. So this potential solution is SETI. Let's move ahead. Let's try and see what SETI is. Obviously, I don't have time to go into all the details, but what I can tell you a little bit about it, because this is going to be an only talk about it, so I do want to give you some background, because I'm not sure all of you might be familiar with what SETI is and what we exactly do in the field of SETI. So let me take a slight diversion and talk about SETI. So what is SETI? I'm sure all of you have wondered about our place in the universe, like, are we alone? When you look up in this night sky, remember this: all the stars that you see have planets around it. Now we know that. If you have asked this question maybe a decade ago, we had no answer. But now, based on what we have found, the number of extrasolar planets we have found, it is almost certain that any star you see in the night sky have planets around it. So obviously the question is that whether life is unique to our Earth is unlikely. There has to be other life there. And once you have life, evolution is pretty common. Like on Earth, life finds a way. It got destroyed multiple times. There has been a multiple sort of large extinction event, at least 6 that people can able to figure out. And in all cases, life survived and it evolved. So once you have life, it will evolve, it will become intelligent, and eventually you should have highly technologically advanced life, most like in at least a large fraction of them. So how do you find them? So this is our Milky Way galaxy. Let's say you have a planet on it which has life. Over time, that life develops intelligent, that becomes technology, and technology also produces radio waves. Radio waves is one of the signature of technology. So when you have life, they're producing radio waves. These radio waves are not bound to a planet. Even if they have been used for communication, they are also traveling in space. So we have multiple of these civilizations living in our Milky Way, all producing radio waves. These radio waves are traveling in Milky Way, and here is Earth. We are sitting here, we are also producing our own radio waves. It's possible for us to encounter these radio waves and capture it, and basically find if there is any technologically advanced life there in the universe. So we use powerful radio telescope. This is a telescope called Green Bank in West Virginia. It's 100 meter in diameter, it's massive. As I think what Greg talked in the morning, the amount of radiation we require for us to basically do any meaningful science is extremely low. So for that, you need a big antenna. So that's how we try to solve the problem. Are we alone? What kind of signal we are searching for? Very briefly, we are searching for different kinds of signals, whether it could be like a deliberate transmission or any kind of leakage radiation. You may ask this question, like what radio waves we are generating, is it possible for those radio waves to be detected by ETI? And the answer is yes. If you talk about the planetary radar signal that we produce, they are so powerful that they can be detected by the same size telescope that transmitted it. For example, Arecibo used to transmit very powerful radio waves. You can detect that kind of radio waves all the way to the other end of the galaxy. Imagine that. We sitting on this tiny dot here on Earth, we are able to produce radio waves that is possible to be detected all the way across the galaxy. Now, the same argument applies for ETI as well. They can also have powerful transmitter for detecting asteroids in their own solar system. That radio waves are traveling in space, and so you can detect them. Not just with that kind of powerful radio waves, even the leakage radiation from mobile phones. So if you take, as Greg also talked about in the morning, if you take the collective transmission of all the mobile phone towers on our planet, it's not as high as the planetary radar, but it is high. It's like 10 to the power 9 volts it reaches. So it is possible for a highly advanced civilization to detect that kind of leakage radiation. So that's what we are trying to do. Just an example, one of the kind of signal we are searching for is narrowband signal, where you put a lot of energy into only few frequencies. This is, as far as we know, there are no natural sources that produces signals like that. So if you detect a narrowband signal, which is sort of coming from an extraterrestrial source, you certainly know that it's been produced by technology. And if it is not our technology, then it's extraterrestrial technology. And we are searching across all different parts of the sky. We are looking at all nearby million stars, our Milky Way galaxy, as well as other galaxies as well. And this search is currently being carried out across almost every telescope that you can possibly imagine. Large number of them are currently collaborating with this program that I work with called Breakthrough Listen. And Breakthrough Listen basically conducts SETI research on all of these observatory. The other program that I also work with is SETI Institute called the Allen Telescope Array and the Very Large Array in New Mexico, which are also at the forefront of this research. And not just that, we are also in a process of basically doing a design study of establishing a radio telescope on the far side of the moon. Because no matter what you do, you cannot escape satellites. They are going to produce interference for us. They are going to produce signal that we are searching for. So the best place for them to set up an instrument to do proper SETI is the far side of the moon. So there is a funded research right now where we are doing a design study of a radio telescope on the far side of the moon. Okay, so that's all about SETI. I hope you got the very quick overview of what exactly SETI is, how we are basically trying to search for extraterrestrial intelligence. All right, so next comes the AGI SETI, it's a short form call for the project that I'm going to talk about, in which we are designing a curriculum for community colleges. And there are 3 different aspects of this curriculum. We are designing lecture notes, we are designing workshop, and then we are also designing GNU radio-based labs. So I'm going to go with each of this module. So let's talk about, so this is our website. I hope all of you will be able to kind of visit that. All our modules that we have basically designed are on there. You can look at different, basically our goal is to design different modules and not design one particular course. So we have a course on like basic introduction to electromagnetics, what exactly are electromagnetic waves, and this is a very popular course in a lot of community colleges. So introduction to astronomy is there, different kinds of radio waves that we are searching in the field of SETI. We have designed GNU radio-based labs, and you can actually download the GRC files from our website, and you can play with in the classroom. Also, introduction to radio astronomy, SETI efforts around the world. The most important thing that we are really proud of is that we are able to also give access to these community colleges for our telescope. So we have this Allen telescope array, so we are also able to provide direct access to a lot of these community colleges to come out at the site and basically conduct observations. So this is, as Simon mentioned, one of the workshops that we conducted earlier this year, where we invited 5 or 6 community college instructors to come out at the site and carry out observation using the antenna, using the array itself, and then they could basically teach their student. So students get very excited if they actually get a hands on a real radio telescope. So that's our primary goal. I'm not going to talk too much about it, but the telescope that we have used for this is the Allen telescope array. It's a fantastic instrument, but Luigi Cruz, who is also in the audience, is going to talk more about the ATA tomorrow. So kind of keep that in mind and do come out for that, where he will go at length about what ATA is. But it's basically an array of antenna. It's a 42-meter antenna. 42 sort of antenna, 6 meter in size. It goes from 1 to 10 gigahertz in frequency coverage, and it's the primary sort of the purpose of the telescope is to search for life. It is in the Northern California, and it is actively searching for all kinds of extraterrestrial signal that we could possibly think about. So what are the different labs? I'm just going to give you a couple of examples, obviously not with the limit amount of time. One of the labs we have designed is detecting Voyager. So Voyager, as you know, is a space probe that was launched way in the 70s, and it is at the furthest man-made object, as you know, right? It has already crossed the boundary of what we call the solar system, and it's reaching into the sort of interstellar space. You can detect it using powerful antenna. So we have basically recorded data from Voyager, and we basically can play it back. So this is a lab that we have designed for community colleges where they can actually get the data from our website, and with a very simple GNU data toolbox, they can build, they can play back the signal that we have received from Voyager. And they can look at the carrier wave, they can look at the sort of the sidebands, play with it. We have also added something else extra, like you can demonstrate to students, like as the signal, as the sort of the source travel further out, the signal strength decreases by basically R square, right? So you want to, if you want to explain that concept, you can do that. So in a GNU radio, you can move and you can basically simulate different distance of Voyager, and you can actually simulate how the signal strength actually decreases as the Voyager move further and further away. So if you want to explain something this like to your student, it's very helpful. So again, going back to the live observation with the Allen telescope, so that was what we did with the recorded data. But as I said, we have also designed specialized graphical user interface just for the community colleges. Because as a radio astronomer, I know how to operate a radio telescope. But it's a long, lengthy process. There's a lot of, one needs to have a little bit of expertise in order to go through everything in order to operate a radio telescope. We don't want to make instructor go through that. We want to make it as simple as possible. And for that, again, credit goes to Joel, who is also in the audience, who has designed this graphical user interface to actually control the telescope with just 3 clicks. So you can configure the telescope, give a command, and you can just let it go. And the telescope basically conducts and takes the data for you. So it gets very easy. And we actually did this trial run in our workshop. And I think all the instructors enjoyed playing with it, and they were able to kind of collect data. And the most important thing is that the data that they collect are in a format that can be played back with GNU radio. Like typically the radio telescope data we collect is a slightly different format. It's called filter bank, but those are not very difficult to play with the GNU radio. But here we are actually collecting data that can be played with GNU radio, so they can do anything they want with the data. They can do any kind of fast Fourier transform. They can extract any kind of information they want within the GRC blocks. Another example, as Simon mentioned, about detecting natural hydrogen from Milky Way. So this is an experiment we did, and it also brought a lot of interest among students, because when students actually clicks on the telescope and they can see the telescope move, if they are at the site, it's even better. But even if they are not at the site, we have a camera set up there so they can actually see telescope move. And most importantly, when the telescope moves on the part of the galaxy, what you see, you start seeing the natural hydrogen from the Milky Way. And that's fascinating for students to really see that for the first time, that it's like as if you're looking through a telescope through your eye. This is a radio telescope. It's actually letting you see the universe, letting you see the distribution of hydrogen in our Milky Way. So this lab also kind of was very popular, and we were able to conduct this with our community colleges. So that's, I think, about final what I had to speak. Just in summary, as I mentioned, we had a couple of challenges. We had a problem of like, how do you motivate students? How do you basically bridge theory and practice? And we hope that by providing all of these different topics, we were able to at least solve a couple of these challenges. And I thank you for your attention. I'd take any question.
I don't know who to direct this question to, but do you have collaborators outside of the US as well? Or is there an option for collaborators outside of the US to collaborate in the college, the NASA college network?
I think so.
Not directly, because through NCCN, being a NASA-funded program, it has to stay in the US. We do have some of the subject matter experts internationally. There's no limitation on that, as long as you're working with NASA data of some form, and that's just about every astronomer on the planet. We very much welcome those subject matter experts joining us, but at the moment we are limited to the US.
Yeah, hi, thank you. I see you're collecting data from Parkes telescope, which is in Australia. Is that, so surely there must be some access to collect some of that data from
Yes.
an Australian perspective?
Yeah, so Breakthrough Listen program that I mentioned earlier, when it was launched in 2016, we actually use Park quite a lot. In fact, 20% of the telescope time was used for SETI from Parkes. So it is one of our primary, what we call, observing facilities till today. So yes, we use it a lot.